Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on similar matrices. So two matrices A and B are said to be similar if there exists another invertible matrix P such that A equals P times B times P inverse. We can post-multiply each side of this equation by P to get the equivalent equation A times P equals P times B. So because of the way matrix multiplication works, in order for this equation and this equation here to be true, A, P, and B necessarily need to be square matrices of the same size. So I want to point out here that similarity is not unique. Any given square matrix A is similar to lots of different matrices, and even the matrix P is not unique. If A and B are similar, there are actually infinitely many matrices P that will do the job. If you change this matrix P, though, you'll have a commensurate change in P inverse. So it turns out that if two given matrices are similar, they'll have the same determinant, rank, and trace. They'll also have the same set of eigenvalues, but not only that, if two matrices A and B are similar, the multiplicities of the eigenvalues will be the same, the algebraic and geometric multiplicities. So it isn't always easy to tell whether or not two matrices are similar. So the text in black sort of helps us rule out similarity. So for example, if we're presented with two matrices, square matrices of the same size, we might first check their trace, the sum of their diagonal elements. That's the easiest thing to check. Now, if their traces are equal, it doesn't mean they are similar, but if their traces are not equal, that means they are definitely not similar. So similarly, we could also, after checking their trace, check their determinant and check their rank. The rank of a matrix, by the way, is the number of linearly independent columns. And then if all of those are the same in both matrices, then we might check the eigenvalues and their multiplicities, which of course is a lot of work. So it isn't easy if you're given two matrices that are similar, it isn't easy to actually tell that they are similar. So we'll look in the lesson at why all of these things are the same in similar matrices, but let's just look at one of them for an example. So let's look at rank. So as I said, the rank of a matrix is the number of linearly independent columns. So the reason the ranks would be equal is because the rank of A, because A is P times B times P inverse, this equation will be true. Now, the reason that A and B will have the same rank is that if you multiply a matrix by an invertible matrix, you don't change its rank. So that text in blue is saying what I just said. So the rank of a product matrix XY is the same as the rank of Y if X is invertible. That's how you read that. And the opposite works as well, that if Y is invertible, then the rank of XY will be the same as the rank of X. So obviously in our original equation, P is invertible because it has an inverse. So using the facts in blue, the rank of A will just be, so the rank of PB is just the rank of B, because P is invertible, and the rank of B times P inverse will be the same as the rank of B, because P inverse is invertible. So that's how we get rank A equals rank B. If two matrices are similar, then they have the same rank. So like some of the other things in the black text, the other direction doesn't work. So if two matrices have the same rank, they may not be similar. If two matrices have the same determinant or the same trace, they may not be similar. So it's a little different for eigenvalues. If you have two square matrices of the same size and they have the same set of eigenvalues, but none of the eigenvalues are repeated, then the two matrices will be similar because they'll both be similar to the same diagonal matrix. Okay, so just letting you know that if two matrices have the same determinant, rank, or trace, they still may not be similar, but there are times where if they have the same eigenvalue set, then they will be similar. So it turns out that similar matrices represent the same linear transformation. So let's have a look at what that means. So let's look at these matrices on screen. So it turns out that the matrices A and B are similar to each other. Note that they both have the same trace, which is 5. They both have the same determinant, which is 6. So because both are invertible, they have a non-zero determinant, that means that each of their two columns must be linearly independent. So they have a rank of 2, and it turns out that they will also have the same eigenvalues of 2 and 3. So it isn't obvious at all just from looking at A and B that they are similar, but it turns out that if I define P as this matrix, I have the situation A equals P times B times P inverse. So A is similar to B. I've put P inverse there just for convenience. So because A and B are similar, they represent the same linear transformation. So let's observe what they do to, say, a vector 2, 3, which is, of course, in R2. Now, when I say the same linear transformation, and that's how it's reported in maths literature, it doesn't actually mean they take the same vector to the same vector. So it is not the case that AX equals BX. So what exactly do I mean? Well, it turns out that this P times B times P inverse can be seen as a change of basis. So when we look at something like X equals 2/3, what we're really sort of assuming implicitly is that we're working with the standard basis for R2. So you can see that X, if it has the coordinates 2, 3, can be written as 2 times the first basis vector plus 3 times the second basis vector. But what if we're not using these two basis vectors? What if we're using different ones? Then the matrix 2, 3 would no longer represent 2 times the first basis vector plus 3 times the second basis vector. So let's look back at this matrix here, P. Now, P is invertible. It always needs to be for a similarity transformation because of that P inverse term. So that means that its two columns will form a basis for R2. So it turns out that if we were using these two vectors, the columns of P, as a basis for R2, then we can write our original vector 2, 3 as 1/3 times the first basis vector plus 7/6 times the second basis vector. So it's like we've transported it to another version of R2, and 2, 3 would be the vector with coordinates 1/3 and 7/6. So if you like, when we're using the standard basis vectors, 2/3 is the same as this vector here is when we're using these two vectors as a basis for R2. So what we're saying here is that A acts on this vector in the same way that B acts on this vector. So let's have a look at that. So let's say I have my vector X equals 2/3 as normal, 2 times the first standard basis vector for R2 plus 3 times the second standard basis vector. So if I times that by A, I just do normal matrix multiplication, I get AX is equal to 16, 14, right? But if instead I multiply X by P inverse, now the reason I do P inverse is that if A equals P times B times P inverse, AX equals P, B, P inverse X. And when you're doing this multiplication, if we're going to do matrix vector multiplication, we need to do this first. Then multiply the answer by P, then pre-multiply the answer by P. So if you multiply P inverse times X, you get precisely this vector here. It's like a change of basis. So these two are essentially the same vector, just using a different basis. Down here, we're using the basis that is the two columns of P. So how does B act on that? Well, we next times it by B. So we take our P inverse X and pre-multiply by B, and it turns out we get the vector 2 2/3 and 4 1/3. So what does this have to do with anything? What does this vector do? Well, let's look at this one here, 16, 14. So up here, in this version of R2, we're using the standard basis vector. So that's 16 times the first basis vector plus 14 times the second basis vector. But down here, we're using different basis vectors. So lo and behold, it turns out that 16, 14, that vector, when written in terms of these basis vectors, is 2 2/3 times the first basis vector plus 4 1/3 times the second basis vector. So sort of like in this version of R2, this vector and this vector are sort of the same when you write them as the linear combination of basis vectors. Now, if we take this vector here, which is B times P inverse times X, if we pre-multiply that by P, we get P, B, P inverse of X. We get back what we started with. So what essentially happens with a similarity transformation is we take our vector, we sort of write it in a different form, then we perform the same linear transformation to it as A would perform, and then we change this form back into the original form. So as an analogy, I want you to pretend I have this friend who's a doctor, and this doctor, for whatever reason, is biased. He only heals you if you have blonde hair. So if you're someone with blonde hair, he can just say, apply the matrix A to you and heal you. The end result is you're a blonde who's healed. But what about if you're not blonde? So let's say you're really sick and you want to see this doctor. Well, what you could do is you could dye, let's say you had black hair, you could dye your hair blonde. So that's sort of like, in this case, applying the matrix P. Now that you're blonde, the doctor will heal you. So A and B are sort of doing the same thing. And then after you're healed, you might undo dyeing your hair blonde, so you'll dye your hair black again. That's sort of what is going on here. The matrix P is just changing a vector so it's the right form. So if you're the vector, in this case, P was dyeing your hair blonde, so your hair was of the right form to be healed. And then as you saw, A and B did the exact same thing, and then P inverse just undoes P. In this case, it turns you back to your original form. So whether you apply A or PB, P inverse, the result is the same. You end up being healed. Whether you had blonde hair to start with or you had black hair to start with, if you apply either of these, you are healed. So now we're going to move on to a special case of similarity called diagonalization. So a matrix A is said to be diagonalizable if it is similar to a diagonal matrix, which we will call D. So remember that a matrix is diagonal if all the elements off the leading diagonal are zeros. So a matrix is diagonalizable if and only if it is non-defective. So we came across this word before when we were doing eigenvalues and eigenvectors. So remember, non-defective means that that every eigenvalue of the matrix has the same algebraic multiplicity as it does the geometric multiplicity. So let's look at this matrix here. So note that A is actually an upper triangular matrix. So the eigenvalues of A will just be the diagonal elements. So the only eigenvalue of this matrix will be lambda equals 4. Because it's repeated as an eigenvalue, it would be a double root of the characteristic polynomial. The characteristic polynomial here, so this being the characteristic polynomial, it has algebraic multiplicity of 2 because it's a double root. Now let's find the eigenvector or eigenvectors associated with this eigenvalue. Remember, to do that, what we want to do is solve the equation A minus the eigenvalue times I. We want to find a non-zero vector x such that that results in the zero vector. So here's 0 and x are vectors. So a minus 4 times I, you just subtract 4 from each of the diagonal elements and you're left with this matrix here. So we want to find a vector x1, x2 so that we end up with the 0 vector. This is an easy one to solve because our matrix here is already in reduced row echelon form. So x2 has to be equal to 0 because when you multiply together this row and this column, you end up with minus 1 x2 equals 0. So that means x2 is equal to 0. But because each time you're multiplying by x1, you're multiplying by zeros only, x1 can be anything. What we can do is write our solutions in terms of x1. So our vector would be x1, any number for the first entry, but the second entry must be 0. So we can just take the eigenvector 1, 0. So this is an eigenvector corresponding to the eigenvalue lambda equals 4. Any scalar multiple of this vector will also be an eigenvector. So there is only one linearly independent eigenvector corresponding to lambda equals 4. So because there's one linearly independent vector, its geometric multiplicity is 1. So because this matrix has an eigenvalue whose algebraic multiplicity exceeds its geometric multiplicity, this matrix here is defective and it is not diagonalizable. It is not similar to a diagonal matrix. So I'm about to get rid of all this working out on the screen, so please pause and copy down if you need. So that was an example of a matrix that's not diagonalizable. So when a matrix is diagonalizable, how do we actually write it? How do we actually find the diagonal matrix to which it is similar? Well, let's have a look. So here, if A and D are similar, we can write A equals P D times P inverse. And once again, we can post-multiply each side of the equation by P, and we get A times P equals PD. What I'm going to do is I'm going to write matrix P in terms of its columns. So let's just say it has n columns. It will be P1, P2, all the way up to Pn. And I can do that on the right-hand side as well. Here, each P1, P2, P3 is a column of P. So D is a diagonal matrix. So it's going to look like this square matrix, and I'm just going to call each of its diagonal elements lambda 1, lambda 2, all the way to lambda n. So all these matrices are the same size. So there will be n diagonal elements of D. All the other elements of D will be zeros because D is a diagonal matrix. So what actually happens if we multiply these together? So each of these P1s, Pn's are columns. They can be thought of as vectors. So if I multiply by A, I'm just going to get the matrix whose columns are A, P1, A, P2, all the way to A, Pn. But if I multiply on the right-hand side, So remember, I go across by down. So if I multiply across by down, so the first column of this resulting matrix will be P1 times lambda 1, but all other entries in that column will be 0 because all the other entries in the first column of D are 0 except the first one. And similarly, if I go and I multiply across by down to get the second column, so I go across here by down, all will be 0 except the second entry, which will be lambda 2 times P2, and so on. The last element will be lambda n times Pn. So hopefully now you're starting to think about eigenvalues and eigenvectors again. So for this equation to be true, we have A times P1, but hang on, P1 was just a column vector. That's equal to lambda 1 P1. This just means that P1 is an eigenvector of A, and lambda 1 is its associated eigenvalue. Similarly, A times P2 is equal to lambda 2 times P2. P2 must be another eigenvector, and lambda 2 its associated eigenvalue. So what actually happens is when a matrix A is similar to a diagonal matrix D, that diagonal matrix just has all the eigenvalues of A on its diagonal and everything else is equal to 0. And the matrix P is just the matrix of eigenvectors. Hopefully now you also see why a matrix is non-diagonalizable if it is defective. Because if we tried this process, that would mean that if A is an n by n square matrix, it would not have n linearly independent eigenvectors. So that means the columns of P, if we tried to set it up like this, would not be linearly independent, and P would not be invertible. And of course, you need P to be invertible for this similarity transformation. So how to actually diagonalize a matrix A? You just set up a matrix P that is the eigenvectors of A and a matrix D that is the eigenvalues of A. Now, when you're setting up P, it doesn't really matter the order in which you put the eigenvectors, but when you're setting up D, you have to make sure that the first entry, the 1, 1 entry, corresponds to the first column, the first eigenvector. And then you have to make sure that the second entry is the eigenvalue that corresponds to the second eigenvector, and so on. So actually, it's quite easy to diagonalize a matrix A. We don't need to do anything that special to try and calculate P. It's just going to be the matrix of the eigenvectors. So let's look at a quick example. So let's look at this matrix here, A, that we saw earlier in the video. We are going to diagonalize it. So the first thing we need to do is find the eigenvalues. So we calculate the characteristic polynomial in the usual way. It's the determinant of A minus lambda I. So now we need to find the roots of that polynomial. Of course, this one factorizes quite nicely into this. So the two eigenvalues of this matrix are lambda equals 2 and 3. So as we have seen previously, distinct eigenvalues correspond to linearly independent eigenvectors. So if an n by n matrix has n distinct eigenvalues, it will definitely be non-defective because each of its eigenvectors will be linearly independent. So here, the matrix is definitely non-defective because each of its eigenvalues is distinct, and therefore it will be diagonalizable. So now we have to find the corresponding eigenvectors. So we're not going to do anything different than what we have been doing. A minus lambda I times some vector gives us the 0 vector we have to solve for x. So, of course, we can't multiply by the inverse of this matrix, because when we're dealing with eigenvalues and eigenvectors, this matrix is always singular. It's always not invertible. By the definition here, the characteristic polynomial, determinant is equal to 0. So what we might do instead is row reduce this matrix. So now that we've row reduced the matrix, we see there will be infinitely many solutions. So we have 1 times x1 minus 2 times x2 is equal to 0. So of course that means that x1, the first entry, is double the second entry. So any vector that satisfies that, where the first entry is double the second entry, will do. So for simplicity, I am going to choose the vector 2, 1. Of course, it won't matter if you chose, say, 4, 2, or 8, 4, or minus 10, minus 5 instead of this vector here. That would change the P matrix, but there will be a commensurate change in the P inverse matrix. So that is my first eigenvector. So I'm going to rub out what's in red. Please pause and copy down if you need. So I need to do similar job now and find the eigenvector that corresponds to the eigenvalue lambda equals 3. So once again, I row reduce the matrix to try and solve for x1 and x2. So I end up with x1 minus 1.5 lots of x2 is 0. Or if you like, x1 is equal to 1.5x2. So any vector will work now where the first entry is 1.5 times the second entry. So for simplicity here, I'm going to choose the vector 3, 2. So again, you can choose any scalar multiple of that, doesn't matter. So we now have the two linearly independent eigenvectors. There's only two of them. I know they're linearly independent because neither is a scalar multiple of the other. So my matrix P is just going to be those eigenvectors put together. So I'm going to put 3, 2, and 2, 1. And of course, I can calculate P inverse in the usual way. So now I set up matrix D. So it's a diagonal matrix with the eigenvalues on the diagonal. Now, because I put this vector here first that corresponds to lambda equals 3, I need to put that as the first eigenvalue in the diagonal matrix, and then the second eigenvalue goes second. So these are the matrices P, P inverse, and D such that A is equal to P times D times P inverse. So it turns out this diagonalization process is very useful when calculating powers of A. So I'm going to get rid of the red writing on the right-hand side and show you why that's the case. So the reason for this, it turns out that when you raise a diagonal matrix to a power, all you need to do is raise each individual element to that power. This only works for diagonal matrices. So d squared, for example, I can do that easily. Just raise the first element to the power of 2, the second one, and so on. And of course, if I wanted to, say, calculate d to the power of 4, just raise the first element to that power and the second element to that power. So that helps us greatly when I want to calculate a to the power of 4. So remember, a to the power of 4, because a is p d p inverse, is just this times by itself 4 times. But remember, matrix multiplication is associative, so I can put the brackets wherever I want. So this P inverse and P, they will cancel out, and this keeps happening. You can see this happens in a chain. So what I'm actually left with is P times, now there are 1, 2, 3, 4 diagonal matrices in a row, times by P inverse. So this is a very easy product to calculate. All I have to do is multiply P by d to the power of 4, and then multiply by P inverse. And this is made easy. It's much easier than multiplying A by itself 4 times, because raising a diagonal matrix to a power is easy. So to calculate a to the power of 4, I just need to multiply this matrix by this one and then by this one, and I get this matrix here. But it's so much effort to perform this calculation if the matrix has been diagonalized. Alright, sorry for the long video. This has been the luckiest maths teacher in the world. Have a great day.